So let's continue. Now, in my class slides, you have a lot of examples according to the order and so on. In my this lecture, the fourth lecture today, in molecular catalysis, I tried to condense it in a way that I skip some details or examples, but give you just the main messages. So we start now from, again, mechanistic consideration of hydrogen evolution, and we start from, now it's a molecular compound. And so here I use M to represent the molecular catalyst, okay? What is important to recognize that to make hydrogen in molecular catalysis, your intermediate, how it works, basically there are two main pathways. One is that you have two metals. I call it bimetallic pathway, but you understand, two metal hydrides. Okay, now in molecular chemistry, you know the hydrogen can be a ligand. We normally call it hydride, okay, connected to a metal. Now, two metal hydrides can come together to make hydrogen. Okay, in this case, the two hydrogen ligand behave effectively as a hydrogen radical. Okay, and so in this process, actually M, the compress, the oxidation state of M, in fact, decrease by 1. Okay, it's because you consider hydrogen now as a radical instead of H minus ligand. So you basically have a reduction of metal by 1. So in this process, it's a whole process as if two hydrogen radical come together. We call it a bimetallic pathway. The other possibility is this hydrogen ligand behave as H minus. Okay, that's what we normally consider in organometallic chemistry. If this is H minus, it will be protonated by a proton to make hydrogen, right? H minus proton. And in this process, to keep the charge neutral, then you understand that this guy now has a plus charge. And in fact, in this process, the oxidation state of the metal pretty much does not change, because the hydride behave as H minus. Okay, so that's the two main pathway. The idea is this hydrogen ligand stabilized by the metal complex behave either as hydrogen radical or S minus ligand. Okay, if it's H radical, it's two of them coming together to make hydrogen. If it's H minus, it's been protonated. Okay, so now, so that's the main hydrogen formation pathway. Now, if we look at in reality how these species can be generated, I show you two catalytic cycles. We start from the first one, which is imagine you have a. So this is your species to make hydrogen. This is MH, and if you have two of them coming together, then you make H2, so we write it as one molecule make half a hydrogen. Yeah, so you understand what I mean. Now, in this case, to generate this guy MH from a catalyst compress, how do you do it? You can either reduce it by 1 electron and then protonate it by a proton. Okay, you make a metal hydride, or you can protonate it at first and then add the electron. Okay, but in any case, that's what you do. You go from M to MH. Yeah, and so now if you protonate it and then reduce it, or you reduce it or protonate it, it depending on the catalyst and the structure and so on. Once you get this intermediate, you make hydrogen, you regenerate your metal hydride. So that's good. The other pathway is that you have the intermediate MH, you protonate it. Okay, you get hydrogen out, you get M plus. Okay, how do you go from M plus back to MH? You first reduce it to M, and then you either reduce it again to M minus and protonate it to make MH, or you protonate it to MH plus and reduce it to MH. Now, again, the order of electron or proton addition and so on, it pretty much depending on your system. Yeah, and but you can see in general, in either pathway, you have 2 electrons and 2 protons to make hydrogen. Okay? Well, actually, in this case, you have 1, you make half hydrogen. So 2 electrons, 2 protons to make 1 hydrogen. In this case, you have 2 electrons, 2 protons, you get 1 hydrogen. So you can follow the logic. And so, regardless of the nature of the catalyst, the ligands, and so on, pretty much you can use this kind of scheme to explain the mechanism. So there are a few different pathways to let's say 4 major pathways to hydrogen evolution by molecular complex, but you don't go more than this. Okay, so that is to say, if you understand this, you pretty much can use this mechanistic framework to investigate all molecular catalysts and to realize what they are doing. And so that will be the fundamental steps in hydrogen evolution by molecular compounds. And here I show you the first example, which is old, but in the slides you have a lot of explanations about it. I just come to the conclusions, okay, which is this ion compound. Okay, you understand that there are some details of this mechanism which may still be subject to further study, but I give you as an example, yeah, to show how a molecular catalyst works. This was studied a long time ago, published in 1996 already, which is, I don't know, 20 years ago. Now, it's using a very simple complex, tetraphenylporphyrin. Yeah? This is a very simple porphyrin compound. It's an iron complex. The iron 3 chloride can be made. Okay? It's also very well studied. Iron 3 chloride can be reduced. When you reduce it, the chloride goes off. This is actually a reversible reaction, so you make an iron 2. Okay? In the iron 2, you have the ligand. I use this to represent the porphyrin. Yeah? And so you have this iron 2. Okay? You can reduce iron 2 to iron 1. You then reduce iron 1 to iron 0, formerly iron 0. Then you protonate proton. You make iron 2 hydride. Okay. Now this step is probably really known in organometallic chemistry as oxidative addition. Okay, because normally when you put a hydrogen on a metal in a coordination compound, you consider them as a H minus. So go from H plus to H minus, you need 2 electrons, right? And who gives you 2 electrons? It's this iron that gives it. So you make iron 2 hydride. You can reduce it to iron 1 hydride if you want, and do this chemistry. But it's already known that the iron 2 hydride in this system can be protonated to make hydrogen. Okay, so then you make hydrogen. In this process, you don't change the oxidation state of the metals. You have iron 2. Okay, now, so you have iron 2, and how do you generate a catalytic cycle like this? What you need is to reach iron 1. You can either give the electron by the electrode, or because you are in a homogeneous solution, you have a lot of this iron 0 species also around. If this step is slow, you have some extra this guy can react with iron 2 to make iron 1. This is also possible. And so it's shown in this study that the mechanistic pathway goes like this. Okay? And so this is one example of one of the 4 pathways of hydrogen evolution by molecular compound. And they study it, and they have good evidence this is the case. What they done is basically they do electrochemistry, and then they fit the electrochemical data with this mechanism, and then they see a reasonable fit. They also can follow actually these 3 steps by electrochemistry and so on. And I will just show you what the data they have. So I said that these 3 electron transfer step is really easy to identify in a pure cyclic voltammetry of these ion compounds. So you can see basically they have this well-defined species. So you know that this is involved. Now in this peak, they see a catalytic wave that is I don't know if I have an overlay. Yeah, I don't have an overlay. But they basically see this catalytic wave in the peak of ion reduction to ion 0. And so that is the peak. And in order to get these rate constants, they use software to simulate cyclic voltammetry, and we don't have to go into details, but just to say they also get kind of rate constant out by just simulating and fitting the experimental data. So let's example really briefly to show that in molecular catalysis, let me see. In molecular catalysis, it's been studied a long time ago. Using a molecular compound to do hydrogen evolution, and then you can have different pathways. But if you have enough experimental data, you can sometimes understand which pathway it is. It's not easy, but it can be studied. In this example I show you, I also introduce the concept how you can actually determine overpotential in organic solvents for such model catalyst, and I will not get into details of it. In the slides, I have also a full reference to a full paper that tell you how you do it, and so you can do that. But I just need to summarize that in this system, the catalyst has overpotential about 600 millivolt for its catalytic wave, as I already said, in the position that close to the peak column. The tone of frequency is relatively high. According to the fitting of rate constant, you can calculate a tone of frequency under standard conditions. That's about 10 to the 5th. The mechanism is relatively clear. You can follow a lot of them. So that was actually a long time state of the art. I mean, there are other systems, but pretty much have similar performance. They normally have a high overpotential. They have a pretty fast reaction rate, and they seem to be quite clear in mechanism. Now, of course, I should point out that a lot of these molecular systems only work in organic solvents because of solubility issues, and also sometimes stability issues. They are not really stable in water and so on. So we consider them as a model study. Yeah. Now, I should also point out that since 2005, there are a number of other systems that improve upon this state of the art, in a sense that previous system you always have a very high overpotential, and well, actually, for instance, in this case, in a study actually done by myself, we have shown that if you now use the cobalt macrocyclic complex, okay, to do hydrogen evolution, you then actually can reach the overpotential that is very low, below 100 millivolt, and so in a sense that molecular compounds also now are known to be able to do hydrogen evolution under this model condition. Again, this is in acetonitrile, that you can have a low overpotential. So from here to here, what people have shown is basically you can actually shift the overpotential to a really low value, and so that is in terms of this kind of study using molecular compound in terms of performance that we have shown so far. And now you can notice that these compounds are just pure coordination compounds, yeah, and they are good because their redox properties tend to be able to couple to the hydrogen evolution mechanism to do this. Now, I would like to now also really briefly discuss another case because it's interesting, because it merged some bioinorganic chemistry with this study. And again, this is a system working in organic solvents using model conditions, but still it's really good to as an example for catalyst design. And so let's the case of so-called bio-inspired complexes for hydrogen evolution. I should mention to you that already that there are enzymes that can make hydrogen really efficiently for hydrogenases, and I show you the classes of hydrogenases are particularly good for making hydrogen. Okay, now these are bacteria or archaeas, and they have the need. Before Earth was rich in oxygen, it was actually under a different atmosphere. They actually process methanes and so on. So anyway, there are a lot of these kind of old bacteria and archaea. They develop ways that they can process hydrogen. In fact, all of you have hydrogenase in your stomach. They are involved. You have some kind of E. coli, so they have hydrogenase. Now, they are really good catalysts in terms of the measurement on a molecular scale, because the turnover frequency at really low overpotential is hundreds to thousands. Now, at least overpotential, platinum has a turnover frequency only about 100 or something below that. So in reality, in terms of molecular reaction rate, it's of course really, really high. The drawback, of course, they are huge. Yeah, the molecular weight is 50,000 to 90,000. So then, if the turnover frequency times the concentration is your net activity, right? Of course, then they are not really good. But still, from a molecular point of view, it's really interesting. People have tried to make this enzyme, put on electrodes, but the problem with this approach is, of course, they are really fragile and really expensive, but also you cannot put much on the surface because they are so big, right? So you cover it. Now, so this really serves as kind of blueprints for designs rather as catalysts themselves, yeah? And so the part that is so fascinating about it is this high reaction rate at low overpotential. And if we look at the more active for hydrogen formation, which is iron-iron hydrogenase, this is an old picture, but you can actually see the active side. It looks like this. Okay, it's a coordination compound, slightly complicated. This is an iron-sulfur cluster. In enzymes, you have a lot of iron-sulfur cluster. They basically serve as electron wires to deliver electrons. Then you have two ions and something like this, a nitrogen bridged dithiolate. A lot of people make a lot of models that look like this, and that's fine. But they are normally not really active. And this just suggests that these actives, of course, need to be in the enzyme to do things. Yeah? There are other functions, not just the primary active site, but also secondary and the whole outer sphere environment. I show you only one proposed catalytic cycle for hydrogen evolution in this system. It's quite fascinating because I'm not saying that this is the only pathway, but this is one possible pathway. In enzyme catalysis, that can be quite complicated. But this is fascinating because this suggests that this part, iron-sulfur cluster, is involved in the whole redox chemistry. So let's start with, where do we start? We start in the beginning. Yeah, the iron-sulfur cluster is in a 2+ overall charge. Okay, the iron one is iron 1, one is iron 2, bridged by CO and this guy. That's the state. And when you put the first electron in, you reduce iron 2 to iron 1 because among this system, that's the easiest to reduce. Okay, you put the first proton in, they will protonate this nitrogen because it's okay, good to go. So now we have the first step to put the electron and proton in. It looks like this. Okay, that's fine. There are some detailed rearrangement of the structure. Now you put the second electron in. What do you put it? You can put iron 1 to iron 0, but iron 1 to iron 0, the reduction potential is quite negative. So instead, actually put into the iron-sulfur cluster. The whole iron-sulfur cluster used to be a 2+. Now it's reduced to 1+. So then the electron is shared among all these guys. Yeah. So you have a so-called mixed valence because now you share it. Okay. Now if you go to this one, that's fine. It's proposed that this proton now is mobile. Yeah. Now in this state, the second protonation, okay, suggests that this guy will be protonated, and this mobile guy, now under this process, will then add to one of the iron. If you add to one of the iron, you turn it into iron 3 hydride. But it turns out that this iron 3 with this reduced iron sulfur cluster, you do an intramolecular electron transfer. So iron 3 will become iron 2, and you give the electron you oxidize the iron sulfur cluster to iron 2 plus. It's just a way to relocate the electron because iron 3 and iron 1 is not really compatible. So you basically just, in this is a complicated process, you see. You actually end up with iron 2 hydride, and this reduced species now is oxidized to iron 2, to 2 plus. Okay? Once you are here, everything is set because then you have a minus, you have a plus, you make hydrogen, and you release it. You go off, and you regenerate a catalytic cycle. For for this iron-iron hydrogenase, you can do the cycle like this to make hydrogen, but you can also oxidize hydrogen to make proton. This is a reversible catalyst, so you can go this direction. Now, one of the main features of this mechanism is that you see a close interaction of this iron with this nitrogen. And it's proposed that's the key, because to make hydrogen, you have a hydride and proton nearby. You make hydrogen. And to activate hydrogen is similar. If you go this direction, you should be like this. So it's proposed that for the enzyme, this is important because it not only involves the ion center, but involves also this so-called second coordination sphere. And this is why this guy is a nitrogen. People have done a lot of study to figure out whether it's nitrogen, oxygen, or carbon, but then they now establish this is nitrogen. And this is proposed as the central function why you actually have a nitrogen, because you involve in the so-called bifunctional catalysis. Now, I already said efforts to make models like this do not really work, because without a protein, it doesn't work as well. And so I want to show you one example really briefly that actually you don't need to do that, but you can use this kind of mechanistic inspiration to design a catalyst. And I show you one rather successful example in this sense. And so let's start by the work of Dubois. Let's show that if you take a nickel phosphine complex, okay, so it doesn't look like an enzyme, but we already said it's using its principle, not using its active site. It doesn't work for how do I say, for hydrogen evolution. Yeah. Then they design this catalyst, which in the first coordination sphere is quite similar. It's phosphine, but they have incorporated nitrogen, okay, into it by sophisticated synthesis. But that's the point. You will be able to do that. You have no nitrogen. The reason why you do this is because with this configuration, the nitrogen is now pointing towards the metal center, right? So you need to have the right angle to do that. And then it turns out this is actually a really good catalyst for hydrogen evolution. And this is the kind of catalytic wave they observe when they add acid into acetonitrile solutions. So again, I said this is done because they are only soluble in acetonitriles and using acid as an organic acid. And the reaction is analogous. It's basically a model for hydrogen evolution in water, but you can already show let this activity. And so the performance, if I summarize, is 280 millivolt. That's somewhere here, overpotential. I haven't taught you how to calculate overpotential in organic systems, but I already said that there's a paper on that you can read. And if you calculate that, and then the turnover frequency is 350, so really fast, and the overpotential is modest. And so, so that's the performance. And if we look at this performance compared to this guy, then there's a huge difference. And the difference, according to this study, is mostly because you now have this nitrogen. And what is proposed, that's the mechanism shown here. That is, you first reduce iron 2. In the graph, you don't, I don't know if you see the oxidation state really well. Yes. So you first get acetonitrile off. Then you, oh no, we had to go this way, yeah? Sorry. You first go to the acetonitrile, you have iron 2. Then you reduce it to iron 1. No, sorry, nickel 2 to nickel 1. And then you protonate it. But it's proposed the proton goes to here because this is protonated. Now it's proposed then you reduce nickel 1 to nickel 0. Okay, so this is fine. Then it's proposed that this protonation of nickel 0 make a nickel 2 hydride. Now, because the hydride and the proton are really close, then you can actually make this guy really easily, and you go off. And by having this as a site for proton to go, you really open this pathway to work very well. While in this case, you can only reduce nickel 2 to nickel 1 or nickel 0, but you can do a similar reaction as in this case. So the fact that you have this so-called pendant arm amine really help in this catalysis. And last example I show you to showcase that you can study some enzymes and give some inspirations and design some molecular systems and having a higher efficiency compared to compounds without this kind of enzyme-inspired design elements. And so this system have been modified a lot by many different groups for hydrogen evolution, and I will not get into details of it. You can read some of these slides. I just want to present you a summary of it in terms of molecular hydrogen evolution catalysis. And I think I show you that actually you can use them as catalyst even at relatively low overpotentials and with high turnover frequencies. From mechanistic point of view, you have 4 possibilities, but they're all quite easy to rationalize. Yeah, you can follow them. They are just different in terms of the order of proton or electron addition, or in terms of the final step to make hydrogen, whether it's metal hydride combination or it's protonation or metal hydride. So mechanistic point of view is quite clear. The diversity and modularity of molecular catalysis is also demonstrated. You can change the ligands and make dramatic change in terms of activity. And I also show you that, I need to put a Z in here. Enzymes offer really inspiration for molecular catalysis, because after all, enzyme is also a molecule, a big one. Now, the limitation, of course, a lot of these systems I show you, they only work in organic solvents when water doesn't complicate things. It's due to the solubility and stability issues. Really often in water, a lot of things decompose, or the function don't work the same. And so these studies are fundamental in nature, right? And so, but you already see that they really give you a lot of inspirations in terms of design of things. And the practical application of these systems haven't been demonstrated. I saw you one example where people are trying to demonstrate a little bit of technical application. Again, kind of in a proof of principle. That is, people have made this catalyst I just mentioned to you, modification of the nitrogen part to connect it to a kind of ester, and with this kind of ester type of derivative, they can actually now graph it into a surface functionalized amine group to make a surface attachment of the catalyst onto a carbon nanotube. Okay, and with that carbon nanotube, they propose that now you can actually do electron transfer and do electrocatalysis. So this is a surface attached approach to the catalyst, and is with a really high surface area carbon nano tube. You can actually achieve, say, a 4 milliamp at 300 millivolt overpotential with this assembly, and they suggest that turnover frequency at this potential is about 3 per second, and you can run it for a number of hours. And so let's just to show you that a potential demonstration of such systems. Of course, it looks good on paper, but this system also has many problems, in the sense that it's awfully difficult to make these kind of things. Yeah, so that's quite expensive, and in terms of long-term stability, it also can become complicated, because under conditions, this kind of attachment can be a problem. But it's just to show you that there are some technical demonstration of the applicability of such systems. So with that, I will actually summarize for the whole chapter on hydrogen evolution. I hope I show you examples of different kind of research in this area. I already mentioned that precious metal can do the work, but they are not. They are too precious, and there are many groups in the world doing intense research in different areas, both heterogeneous and homogeneous, and some people even doing enzymatic studies. We now have a lot of progress in this area, and these kind of methods and technologies have been established for future studies. I also show you typical methods that encountered in this research, especially in terms of electrochemistry and electrocatalysis. And so, so this is still a field of growth for the moment, and hopefully soon we will have the breakthrough, maybe from you, to really solve this problem in terms of catalysis. And with that, I think I finished for this chapter. I also finished for today's lecture.